In this tutorial, I'll go over different strategies to evaluate how good your shape model actually is. Hi and welcome to Coding with Dennis. My name is Dennis. This here is the sixth tutorial in the series on how to create statistical shape models. When it comes to model evaluation, nothing really beats visual inspection of the model's anatomical properties. With Scalismo-UI, we can inspect the individual principal components of the model one by one, as shown also in the previous tutorials. Load in the model and inspect the components. Then try randomly to sample from the model to see if the shapes look realistic and anatomically plausible. And very importantly, check that the model does not produce any kind of artifacts such as self-intersection, inverted surfaces, or similar. Then, as a second step, consider the application where the model will be used and see if an automatic evaluation can be created. This could, for instance, be partial mesh completion. In such a case, you can synthetically remove parts of a mesh and check the model's reconstruction with the ground truth. A good first step for this is to use the training data itself to begin with. So for the training data, we already know that the model should be able to represent it precisely. Then, after it's validated, we can move on to check the model's performance on a test dataset, where we also know the complete shape. And finally, the model can be used on partial data with no ground truth data. This data can of course only be qualitatively evaluated. Now, instead of comparing complete meshes with a ground truth method, another common strategy is landmark-based evaluation. Here the model's ability to identify specific landmark points is checked. For the model, we need to create a landmarks file where the landmarks are placed on the template mesh. Then we extract the position of the same point ID after the fitting. The task is then to compare the landmarks with landmarks clicked manually by a human observer, and possibly other automatic methods if available. Besides qualitatively looking at the model or looking at the model's performance on a specific application task, we can also look at some fundamental properties of the model. First off, if you randomly sample from the model, is the model only able to represent items from the dataset that it was built? Or how different shapes is it able to create? Second, how good is the model in explaining items not in the training dataset? And third, how much variability does the model have and how is this captured in the model? These three properties are referred to as specificity, generalization, and compactness. The metrics were introduced by Martin Steiner in the 2003 paper, Evaluation of 3D Correspondence Methods for Model Building. And this paper has really since become the standard when evaluating statistical shape models. But even though the method provides good insight into a single model, the metrics are way more useful when comparing different models. This could, for instance, be models built on different datasets or built using different techniques. The three metrics, they're usually reported by limiting the model to only use a certain number of its principal components. And then we can create a 2D plot where we plot the number of principal components on the x-axis and the metric that we're evaluating on the y-axis. And now let's go over the vertebra example and see how we can actually calculate each of these metrics for the model. First off, generalization, which is measured on data items not in the dataset. So we'll build a model on 7 of the vertebra samples and test on the remaining 3. So a different and better strategy, in fact, is to average of a leave one out calculation if you have very limited data available. But first, let's define our training data and test data items and build our model to be evaluated. For the training data, we take the first 7 items from the registered folder, and for the test, we take the remaining by dropping the first 7 items. Then we make a data collection of each, and finally create the model to be evaluated from the training data. Then I'll use Scalismo's built-in model metric functionality to compute the model's generalization. To this function, we just need to pass the model and the data collection to be used for the calculation. In this case, our testing data. And now let's call this function with the model limited to a certain number of principal components. For this, we'll use the model.truncate function. And finally, let's plot the output data. Note again that the x-axis specifies the number of principal components that we use from the model, while the y-axis is the average distance in millimeters between the model and the test meshes. In the plot, we see that the model generalizes better the more principal components are used, as would also be expected. If we compute the generalization on the training data, when using all the principal components, the model should be able to precisely describe the data. In other words, have a generalization of around 0. We also see that this is indeed the case. If we, for instance, have a model with 100 principal components, but already after 50, it can perfectly describe both the training data and the test data, this could hint towards some data not being needed in the model. And we can therefore use a more compact model with only 50 basis functions instead of 100 and get more or less the same result out of it. For the specificity, we can use the function available in Scalismo's model metrics. To calculate the specificity value, we pass in the training data and not the test data. We then specify a value describing the number of samples that the function should take. The higher this number is, the more precise the specificity number will be, but it will also take longer time to calculate. So I usually use a value of at least 100. Internally, what is happening is that the function will produce 100 random samples from our model and then calculate the average distance between the samples and each of the items in the training dataset. For the final specificity value, only the closest training data item is used. So in other words, for each sample, the function finds the most similar item in the training data and calculates the average distance between the two. And then finally, it takes the average of all these 100 samples that were produced. For the specificity, we should see that the more principal components that are used, we should be able to create shapes that are further away from the training data. So in other words, a higher specificity value as also found in our case. For specificity, the axes describe the same as for generalization, so number of principal components and average distance in millimeters on the y-axis. And finally, the compactness measures the model's ability to use a minimal set of parameters to represent the data variability. This value here is straightforward to calculate from the variance information stored about each principal component in the model. And what we see is that each added component adds a lot more information to the model. Again, if we had a model with 100 principal components, we might see the value flatten out after some time, suggesting that the remaining principal components provide little to no extra flexibility to the model. While the model metrics can be used to evaluate individual models, they are way more useful when comparing different models. As also described, these models could, for instance, be built from different datasets or using different data techniques to create the models. Another useful area of model evaluation would be to compare the PCA model to different augmented models, as also introduced in one of the previous tutorials. This can help to check if the model is augmented enough to generalize better, but at the same time not too much to suddenly produce unrealistic shapes by having a too high specificity. So in summary, always visualize your models and try to formulate an application-specific validation for your model. Finally, I also showed the commonly used metrics to evaluate statistical shape models: generalization, specificity, and compactness. In the next tutorial, I'll go over different ways to visualize statistical shape models. That was all for this video. Remember to give the video a like, comment below with your own shape model project, and of course, subscribe to the channel for more content like this. See you in the next video.